Hello class, welcome to Stat 1200. I am your instructor William Buellman, and today we are covering section 6.3, the central limit theorem for proportions. Our objectives for today are to construct the sampling distribution for a sample proportion and use the central limit theorem to compute probabilities for sample proportions. In a population, the proportion who have a certain characteristic is called the population proportion. The population proportion is denoted by P. In a simple random sample of n individuals, let x be the number in the sample who have the characteristic. The sample proportion is p hat, which is p with this little arrow above it, which is equal to x over n. Example 1. A computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws out a sample of 100 people and surveys them. It turns out that 35 out of 100 people own laptops. The sample proportion is p hat, which is equal to x over n, which is equal to 35 over 100, which is 0.35. The proportion of people in the entire city who own laptops is the population proportion, P. If several samples are drawn from a population, they are likely to have different values for p hat. Because the value of p hat, the sample proportion, varies each time a sample is drawn, p hat is a random variable and it has a probability distribution. The probability distribution of p hat is called the sampling distribution of p hat. Consider tossing a fair coin 5 times. This produces a sample of size 5, where each item in the sample is either a heads or a tails. The proportion of times the coin lands on heads is the sample proportion p hat. The probability that it lands on heads each time is 0.5 since it's a fair coin. Therefore, the population proportion of heads is p, which equals 0.5. Next, we look at all 32 possible samples that can be constructed. The table on the next slide displays all possible samples of size 5 and their sample proportions p hat. The mean of all the values of p hat is mu of p hat, which is equal to 0.5, and the standard deviation of all the values of p hat is sigma of p hat, which is 0.2236. Here's the table with all the p hats in the different samples. Next, we compare these values for the population proportion of 0.5 and the sample size of 5. In the previous table, the mean of the sampling distribution is mu of p hat, which equals 0.5, which is the same as the population proportion of p, which was 0.5. This relation always holds. The mean of the sampling distribution of p hat is denoted by mu of p hat and is equal to the population proportion. The standard deviation of the sampling distribution, sigma of p hat, was equal to 0.2236. It is not immediately obvious how this is related to the population proportion p and the sample size n. Note, however, that sigma of p hat equals 0.2236, which equals the square root of 0.5 times 1 minus 0.5 over 5, which this is equal to the square root of p 1 minus p over n. The standard deviation of the sampling distribution of p hat is denoted by the sigma of p hat, which is sigma of p hat equals the square root of p times 1 minus p over n. Example 2. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether or not they win a prize. The proportion of tickets that are winners is P, which is equal to 0.3. A total of N equaling 80 people purchase soft drinks between noon and 1 p.m. on a certain day. Let P hat be the proportion that win a prize. Find the mean and standard deviation for P hat. The population proportion was given to us of P, which was equal to 0.30, and the sample size N of 80. The mean of P hat, remember mu of P hat, was just equal to P, which is equal to 0.3. The standard deviation of P hat, sigma of P hat, remember, was equal to the square root of P times 1 minus P over N, which is equal to the square root of 0.3 times 1 minus 0.3 over 80, which is equal to 0.05123. The probability histogram for the sampling distribution of P hat for the proportion of heads in 5 tosses of a fair coin is presented below. We can see that the distribution is reasonably well approximated by the normal curve. The experiment is conducted again, but this time with 50 tosses of a fair coin. As we increase the number of tosses, the sampling distribution P hat is more closely approximated by the normal curve. So if we look at this top histogram, we can see that it's close, but there's some gaps and it doesn't fit quite as well. Versus if we look at this bottom histogram, the gaps are much less pronounced and the curve fits much more closely to this histogram. So as we increase the number of trials, we got a closer histogram to the normal curve. When P equaling 0.5, the sampling distribution of P hat is somewhat close to the normal, even for a small sample size of 5. When P is close to 0 or close to 1, a larger sample size is needed before the distribution of P hat is close to normal. A common rule of thumb is that the distribution may be approximated with a normal curve whenever N times P and N times 1 minus P are both at least 10. This is the central limit theorem for proportions. Let P hat be the sample proportion for a sample of size N from a population with a population proportion P. If N times P is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10, then the distribution of P hat is approximately normal with mean P and standard deviation equal to square root of P times 1 minus P divided by N. Example 3. A sample size of 25 is drawn from a population with population proportion P equaling 0.8. Is it appropriate to use the normal distribution to find probabilities for P hat? So can we use the central limit theorem? No. Since N times P is equal to 25 times 0.8, which equals 20, that check passes, but N times 1 minus P, which is equal to 25 times 0.2 equals 5, that check fails because N times 1 minus P is not greater than or equal to 10. So since that check fails, we cannot use the central limit theorem for P hat. Example 4. A sample of size 110 is drawn from a population whose population proportion is P 0.9. Is it appropriate to use the normal distribution to find probabilities for P hat? So again, can we use the central limit theorem? Again, we have to make 2 checks to see if we can use the central limit theorem. N times P, which is 110 times 0.9, which equals 99, so that passes because that's at least 10. And N times 1 minus P, which is equal to 110 times 0.1, which is 11. Again, that's greater than or equal to 10. So since n times p and n times 1 minus p are both greater than or equal to 10, we can use the central limit theorem and thus say the distribution of p hat is approximately normal. Example 5. According to a recent Harris poll, chocolate is a favorite ice cream flavor for 30% of Americans. If a sample of 150 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.32? First, we check the assumptions. So n times p, which is 150 times 0.3, that's 30% in decimal, which is equal to 45. That's greater than or equal to 10, so that's good. Now we need to check n times 1 minus p, which is 150 times 1 minus 0.30, which equals 105, which is also greater than or equal to 10. So that checks out. So our assumptions have been satisfied. We may use the normal curve. We compute mu of p hat, which is equal to p, to be equal to 0.3, and sigma of p hat, which is equal to the square root of p times 1 minus p over n, which is equal to the square root of 0.30 times 1 minus 0.30 over 150, which is equal to 0.037417. So now we need to find the area under the curve to find the probability that it's greater than 0.32. So the probability that the sample proportion of those who prefer chocolate is greater than 0.32 is 0.32 minus 0.30 over 0.037417, which is equal to 0.53. So that's our z-score. If we look up that in our z-table, we get the probability is 0.2981. So here's a practice problem for you guys. In the 2012 U.S. presidential election, 52% of voters voted for Barack Obama. If a sample of 80 voters were polled, would it be unusual if less than 38% of them had voted for Barack Obama? So you guys go ahead and try this, get the answer. I will show the solution in 3, 2, 1. Here's some scratch work just to show you, checking the assumptions, finding both mu of p hat and sigma of p hat. Here's the z I found. That gives me this probability of 0.0060, which was less than 0.05, which thus this is an unusual event. For you guys, you want to fill in some more details here, make it completely clear and concise. This is just me showing you some scratch work of how the solution would be so you can check and make sure that you got the same understanding that it would be unusual.